column-wise. And this is called, what the community calls, a column store. So I have one file in the database for every single attribute of every single table. Now you see this is going to be attractive because I'm going to compress this thing. I'm going to apply some pretty aggressive compression techniques, and I'll get to that. But first I want to go back to the CPU example that I tried to show earlier. So here again I have my CPU and my L1 cache and my L2 cache and my memory. I have the same query, selecting IDs, names, and balance dues from customers, where I'm looking for customers with a balance due greater than 500. And out there on the disk drive, I've got my column store. I've got my ID values all stored together, my name values all stored together, my balance due. All these things are stored tightly packed. In fact, if you know something about how databases are really built, we cannot update this structure. These things, this is a read-only data warehousing environment. If we have to we're going to pack these values tightly. There's no record header. There's no value header. The values are going to be tightly packed one after another because we're trying to take maximum advantage of that little water pipe coming out of the disk drive. So we don't want any stuff, all the stuff that made it easy to update rows in a relational database system in place, we've thrown away because we're specializing the database system for running decision support, read mostly kind of workloads. Okay, so now we're ready. We bring the first page of balance due into the memory. We bring it in the buffer pool in the normal way. But notice what happens on the first L2 cache miss. Basically, instead of bringing one useful value from memory into the L2 cache on the miss, I bring 3 values. And in fact, 64K byte cache lines, 4-byte values. I'll actually, in a real system, I might bring 16 values in on one miss. Instead of missing on every single record, my misses are going to bring lots of good stuff into the cache. Then I have I'm going to suffer an L1 miss. I'm going to bring those values into the L1 cache, and I'm going to process them there. Then I'm going to have another miss to get the last 2 values on that first page of balance due, another miss, and then I'm going to bring the next page of balance due values into the buffer pool. I'll have a miss on L2, but again, every miss brings good stuff into the cache and not a bunch of wasted stuff into the cache. So if you have an 8K byte page, you'll get 1,000 values per page, not 5, obviously. Okay? If you have a 32K byte page, you'll get 4,000 values on a single disk I/O. I'm not showing the disk I/Os, but I'll come back and I'll give you some examples in a second to do the ID and names. Eventually, to answer this query, and I'll show you how we actually run these kind of queries, how we architect systems in a little bit. To actually run this query, I actually will need to fetch the names and balance due, or the names and the IDs for the customers which have a balance due greater than 500. So let me give a little concrete example to show you what we can expect in terms of performance improvement. So my customer table got 10 million rows. The rows are a couple hundred bytes long. Total table size of 2 gigabytes. The ID and balance due values, just bear with me, are 4 bytes long, and the name is 20 bytes. So there's my query again. Oops, change the balance due to $1,000 instead of 500. In a row store, the execution time may be bound by the disk transfer. So we have 10 million rows, 2 gigabytes total about. At 80 megabytes a second, the query will run in about 25 seconds, assuming you're not using any parallelism. And I meant to say that earlier. I'm looking at how we're going to architect the nodes inside our parallel data warehouse. Okay, so I'm sort of diving into a node. If we use parallelism to run this query on 10 nodes, then we could run it in 2.5 seconds. But we can apply these same column store techniques to every node, and we'll cut the column store execution time by a factor of 10 if we're running on a 10-way Madison appliance. So in a column store execution of this query, I'm going to scan 3 columns, each with 10 million rows, 10 million entries, values, I should say. 280 megabytes total at 80 megabytes a second, 3.5 seconds for a speed up of about 7x. So again, if I'm touching all the attributes, I'm not going to get the same kind of speed up. But if I'm only touching a subset of the columns in a table, I can get dramatic speed ups by reading only those columns that are needed to execute the query. Now, as you're going to see, this column store model allows us to really, really compress the data. And instead of getting a 7x improvement, we might get a 20x improvement, a 30x improvement, depending on how well the data compresses. And I'll come back to that. So summarizing, storing tables as a set of columns can significantly reduce the execution time of certain data warehousing queries. The query I've shown there, select star from customer, is never going to be faster. So if you're always fetching, if the database system is always fetching all the columns of a table, organizing that table in a column store fashion is not a good idea. And obviously, you'll want your database system to be able to store some data row-wise and some data column-wise, depending on how the table is being used. And you can imagine things like the index tuning wizard becoming a column store wizard, to advise you on whether you'd be better off for your workload organizing the table as a row store or as a column store. In addition to reducing the amount of disk traffic that the database system has to perform to run the query by factors of 10, perhaps, the design dramatically improves CPU performance by reducing the number of L2 data cache misses and L1 misses. And as we'll see next, it facilitates the application of very aggressive compression techniques. Now, I'm going to talk in the remainder of my time, which is about another hour. Bill said I had 2 hours today. I know you're just all out there tweeting anyway. So, before when I started teaching, the students in the back read the newspaper. Okay, that was a long time ago. I became a professor in the mid-'70s. I became a professor in the beginning of the mid-'70s. Then, towards the end of my career teaching, they, brought their laptops, and soon I discovered they were just cruising the web. So I became a real jerk and said no laptops. And I don't know what I do, because I thought, pay attention, okay? You're not all getting A's. So now I'm sure if you're a professor, the students are all in the back tweeting. It's like, okay. So I'm going to talk about the following issues in my remaining 25 minutes. I'm going to talk about representation alternatives for column stores. I'll talk a little bit about compression techniques. And there is an entire field of papers that describe even more aggressive techniques that I'm going to talk about. I'll talk about execution strategies, because you can't just, to have a good column store implementation or database system that will support queries on this column store representation requires changing the way you actually execute the queries, and it changes the query engine. You can't just glue this thing on to your database system, as some of our competitors have done. Dealing with updates. Sorry, there's no free lunch when it comes to update. You're going to pay a price. You're going to get great read performance. You're going to get bad update performance. Now I've changed the example a little bit. So now I have a sales table that has just 3 columns to illustrate these next ideas. So quarter, product ID, price. And I've taken this table and I've sorted it by quarter and product ID. And I'd like to talk about 3 alternatives that have been proposed. And there are more alternatives than this out there in the literature. I actually have a couple different ones. I'm going to talk about one that a student of mine and I proposed in a paper in 2005. But the earliest paper sort of describing this goes back to 70, and then a paper by 85. And that was something called DSM, or decomposed storage model. Because composed, when George Copeland and Setrad Koshafian came up with this idea, decomposing things vertically. So in the DSM model, you take this sales table, and again, please notice that this thing is sorted on quarter and then product ID, okay? Major, minor sort. And there are supposed to be about 300 rows in the table for quarter one, and I can't remember how many rows for quarter two right now. That's what those ... So their approach to this problem was to take the table and slice it into these columns, and then to each value in the column, like quarter one, I add a row ID to establish the correspondence between values. So you see that the first row in the table on the left, Q1, 1, 5, becomes 3 different values in 3 different instances of this vertical table, and every one has a row ID 1 glued next to it. And these row IDs, and then the same for the next row in the table before I load it. So again, table on the left is what I'm about to load. The tables on the right are what it looks like after I've loaded it. So every single value gets an extra value associated with it that identifies the correspondence between the different values in the columns. These things are used in query processing to glue stuff back together. Now, you notice that if you've got a lot of integer attributes or small attributes, these row IDs, they probably can't just be 4 bytes. They probably have to be 8-byte integers. They can be pretty big. They can waste a lot of space. That wastes disk bandwidth. Remember this pipe? And they also get in the way of compression. And I'll explain an alternative in a second. Now, the implementation for this actually typically uses a Btree. So this is the logical view on the right here. But the physical representation, typically if you build a database system that uses this storage model, is a Btree built on those row IDs. So here I've shown one of the columns, the column for quarter, in its actual real representation, which would be with an index. So we have row ID 1, quarter 1, row ID 2,